How is data actually stored in a database system? And how does a database system manage a huge amount of data that may exceed the main memory? What's inside the database files? And how does the system find the data that it's looking for? To answer all these questions and more, let's see in this video. Hello and welcome. This is Elhelw, and we are talking about databases. Last time we talked about database systems and how they store and manage huge amounts of data, but how does this data actually get stored physically in the system? Let's look at a database system at a high level and see what are the main components that it has. So looking here, we can see that there is a storage layer at the bottom, and then there's a couple of components like the storage manager, there is the query optimizer, the runtime engine, and then at the very top there are the applications and the users that interact with the database system. So storage is the bottommost layer. This is where the data is actually stored. This is like the base of the database system. Without it, there's no database. And the data is actually usually stored in some kind of like non-volatile storage device. As I mentioned, database systems usually manage huge amounts of data that may exceed the amount of main memory that you have. So there has to be some kind of data movement between disk and memory. All these details about how the data moves and how how this low-level data management happens usually happens behind the scenes, and the database system makes this invisible to the user. So the user doesn't need to know all these details, but we are going to go through all these details. So let's first talk about the different kinds of storage that we have. These are roughly the different types of storage that you may have heard of, starting from CPU registers, cache, DRAM or main memory, and then going to SSD, hard disk drives, and network storage. These are different types of storage. At a high level, we can classify them into two categories, volatile and non-volatile. Volatile means that whatever data that is stored in these storage devices, once the power is off or once your machine is shut down or there's some kind of failure, these storage are wiped clean. So the data is not persisted there anymore. The non-volatile ones are the opposite. Data is persisted there regardless of whether there is power or not, whether you shut down the machine or whatever it is. The next time you start it up, the data will still be there. So that's the main difference between volatile and non-volatile storage. Usually, the volatile storage devices are optimized for random access, which means that you can access any part of the storage at any time and with the same speed and the same performance. So you can access like the beginning of the storage area, the middle, the end, and then come back to the beginning, and that's totally fine. For the non-volatile storage devices, these are usually optimized for sequential access, which means that to get the best performance, you have to read the data in sequence of how it is physically stored. So you just kind of keep going and keep reading that data. The most, I guess, old-fashioned example of that would be like magnetic tapes, where you have to read the data in sequence of the tape. You could potentially go to the beginning or go to the middle, but that takes time and it's a costly process. Same thing applies to magnetic disks, for example, because you have to physically move the head and so on. So that again takes time. So it's best to use these devices for sequential access. For the non-volatile devices, usually you can address individual bytes. So you can say, give me the second byte and then byte number 20 and then byte number 45 and all that. But for the other ones, usually you get pages or blocks at a time. You can't get just an individual byte. So again, this is something to keep in mind when we're dealing with storage devices. In terms of speed and cost and size, these are kind of also go from when we look at the CPU registers, these are usually very small. They are the fastest thing possible, and they are pretty expensive, per unit byte or per unit data there. The more you go towards the other side of the spectrum, things get much cheaper. You always have much larger capacities, and the cost per unit, let's say byte, is much, much lower. That's why you have a lot of that. Another point of reference, if we look at the access times, we talked about the speed, how it's different. So let's say the first level of cache is usually very fast, the access time is 1 nanosecond. And it gets slower the more you go towards the end of disks and so on. A typical SSD would be like 16,000 nanosecond, the access time. The magnetic drive would be like 2 million nanosecond, and so on and so forth. So you can see like the big difference in speed between these types of storage. So from now on, I'm basically going to talk about two types of storage. I'm going to be talking about the disk and the RAM. So the disk is non-volatile. We try to optimize sequential access. RAM is volatile storage. We try to use it for random access, and it's much, much smaller than the disk. So we're always going to be talking about these two going forward. So with all that in mind, what do we actually want to see in a storage medium for a database system? So there are some design goals, like someone designing a database system. What are the design goals for the storage layer there, right? The first thing is that we want to be able to manage data that hugely exceeds the main memory. So, which means that we have to put some data on the disk and then deal with that. And we'll need to also manage the movement between memory and disk. We have to minimize reading and writing from disk. So any disk I/O, because it's expensive, because it's super slow compared to memory, so we need to minimize that as much as possible. That said, we will have to read stuff from disk. So whenever we have to do that, we'll try to maximize the sequential access, sequential reading or sequential writing, because this kind of devices are optimized for this kind of access. So let's see how, again, at a high level, how the data transfer is managed between memory and disk. Let's say we have our memory here and we have some data on disk. The data, as we said, like usually you manage it in terms of pages or blocks. Now the query engine is requesting a particular data page, right? As part of the query processing, it asks for page number 3. So we look in the memory, we can't find it in the memory. So we have to get it from disk. So we'll figure out how do we locate a certain page and all that. But at a high level, let's say we find it. So we're going to bring it from disk into memory. So that's a disk I/O. And then hand over a pointer to that page to the query engine. The query engine can read the data, interpret the data in whatever way it understands, return the result of a particular query that's working on. At some point, we might need to update the data. So it will have to kind of like overwrite some of the data in this page, and then eventually we're gonna write this page back to disk again. So this is kind of like at a high level the kind of operations that we would do at the storage layer of a database system. Now, as I mentioned, we need something to manage this storage in a way that is invisible to the user and invisible to the other components of the database system, right? Anything else, like the query engine doesn't need to know about these details. The query engine will always find the data in memory. So going back to our diagram, again, we pinpointed the storage layer at the very bottom. So right above that, there is a component called a storage manager. So this storage manager is responsible for handling all aspects of the data storage and the transfer and writing to disk and getting things from disk to memory and all that, so that everything above that doesn't need to worry about these details. The storage manager also communicates with the hardware either directly or through the operating system. So the operating system usually provides some APIs that allows software to write blocks or read blocks and so on. So the storage manager may need to interact through these APIs, or some specialized databases may have a way to directly communicate with the hardware. Now, in a database, the data is usually stored as files. Each database system may have its own format, so these formats are specific to each particular system. You cannot take, let's say, the files from SQL Server and put them at Oracle, for example, and expect them to work. So that's not going to work. Each system has their own specific file format. These files are usually not something that the operating system can understand or interact with. For the operating system, it's just a file that has a sequence of bits and bytes. It doesn't know the contents, what they look like, what the format looks like, how to interpret them or how to interact them. So this is the job of the database system itself. Some systems store all their data in a single file. Some others store them in multiple files. If you have a single file, then all the data is there. You don't need to worry about that. If it's multiple files, then the system also needs to figure out if it's looking for something, which file it should look for, and so on. So depending on the structure or the architecture of the database system. So now that we know that we have these files, right? How is the data organized in these files? So each file contains a number of pages. So the data is organized into these pages within the file. What is the page? Page is basically a fixed size block of data. As I mentioned earlier, like usually when we're dealing with disk or any of the non-volatile storage devices, we read data in pages or blocks. So this is what we are talking about. Each page can have pretty much anything in it. So it could contain data related to tables, it could contain index data, it could have log data, it could have catalog data, it could have some other metadata. In the end, they're all stored in these pages. And again, the system would know which pages belong to what. Like, is this an index page, or is this like a table page, or is this like a catalog page, whatever it is, the system will identify them in a way. Each page will have a unique ID so that the system will be able to, retrieve specific page that it's looking for. It will know that, like, page with ID 7 is actually physically stored in that location on disk, and so on. So it can retrieve that page whenever it needs to. The storage manager, as we mentioned, is the component that's responsible for tracking all these pages, tracking which data is being read or written from a page. It also tracks, like, the available space that we have, so that if we need to add more data, it will know where to add this data or what pages have available space to add this data in. Also, one thing to note is that usually the storage manager does not maintain multiple copies of a page. It has a single copy. Someone might ask, okay, what about like replication and things like that? How does that get taken care of? Usually this is taken care of by a different component, like a replication manager or something like that. And that's usually either above or below the storage manager. We did not put it in the diagram that we showed a little while ago. But basically, from the storage manager point of view, each page has only one copy. Whether it has replicas or not, that's handled separately from this. All right, so we have seen that each file contains some pages, right? What do these pages look like? How they are organized within the file? There are different ways to do that. So some of the most common file organizations are heap, tree, sequential or sorted files, as well as hashing files. Each of these has its uses and its particular use cases that benefit from it. The most common one, which is the one that we're going to talk about in more detail, is the heap file organization. This is the one that we usually use to store the data pages. The other ones are used for other things. For example, like the tree file organization is used usually for indexes, for index that have or that allow us to do range queries in particular. We're going to talk about that in a separate video. Sequential or sorted file organization, or sometimes it's referred to as ISAM. This is usually used for batch processing and things like tape storage. We're not really going to get into that. That's a very kind of like, old-fashioned kind of organization. And then there's also like a hash file organization. It's a different type of indexes that are mostly used for equality predicates or equality queries. So again, we're going to focus for now on the heap file organization, which is used for our data pages. What is a heap file? A heap file is a file that contains pages. These pages are unordered. Again, we said that they are already kind of like all have the same size, but there is no significant order between the pages, just a random collection of pages in the file. And the contents of each page are also usually unsorted. Well, okay, so then the question is, how do we locate a particular page? Let's see. Let's imagine this is kind of like a conceptual image of what the file would look like. You have a bunch of pages in the file. Assume for now that the database has a single file and that it is actually ordered, which is the opposite of what we just said. But let's just assume that for now and see how we can locate a page. If they are ordered, and let's say we're looking for page number 3. Because we know that the pages are all the same size, and because we know they are ordered, we can basically calculate the offset of any given page. So the offset is going to be the page number multiplied by the page size. So then we know where is the start of page 3, and we can easily access that page. Now, this is again in the case that we have a single file and that file is ordered. But in the actual heap layout, we can have multiple files, and then each file is also unordered. So how do we find something? Assume that we know the file. So, okay, let's assume that we're dealing with a single file, but we still want a single particular page. How do we find it within the file? We don't know. We can't rely on the offset because the pages are not in the in that order. So there has to be a different way to be able to locate a page. The heap file usually has a additional metadata. It will tell us what pages it has, and also where is each page in the file. It would also have what is the free space in this file. This is stored in something that we call the page directory. So each file at the very beginning of the file, or in some part of the file, usually in the beginning, would have this metadata called the page directory. So the page directory is a special page or multiple pages, and they have things like the location of each page. So you can map from the page ID to where that page is in the file. It could also have the number of free slots per page. We're going to talk about the slots later on, but just think of it as where are the free space within this page where we can add new data. It will also have the list of free or empty pages within the file. Again, that will help us whenever we want to insert new data. So yeah, it could have also other information depending on the system, and each system may want to keep track of more information than that. But that's kind of the gist of the page directory. The page directory needs to be kept in sync with the data pages, right? So whenever we update a page, whenever we delete a page, whenever we add some data, we need to keep this page directory up to date. If it is not kept up to date, then the data could be corrupted. We might add a page, and then if we haven't updated the page directory to reflect this new page, then we may not be able to locate or retrieve this page later on. So we inserted the data, but we have no way of reaching it. Or if we have deleted data, but we have not updated the page directory, and we have not updated the fact that we have now empty space, then we will not be able to insert new data even though there is empty space. So things like that, we have to make sure that this is always kept in sync. Okay, so now that we know that, we can look again at our heap file organization. Now each file has this page directory in the beginning together with the data pages, right? So when we're looking for a particular page, the first thing we're going to do is that we're going to look up in this page directory. The page directory is going to give us the location of the actual page so that we can go and read that page from that location. So this is how this happens. How do we get the page that we want to read, or how do we know which file we want to read from? We're going to get into that in the next video, but for now, assume that there is a way to know that we want to read something from this particular file from this particular page. So now we know what the pages look like inside the file, how they are organized. All right, so we have seen how the pages are organized within a file. How are the data organized within a page? How do we locate a particular tuple? What does the tuple actually look like in storage? So we're going to get into all these questions in the next video, so stay tuned with that and subscribe to the channel to get the updates for the next video. But for now, we're going to summarize what we talked about today. So we started with talking about the different storage types that we have. We described the difference between the volatile and the non-volatile storage, how data is persisted in the non-volatile storage, but it is not in the volatile ones, how some storage devices are optimized for sequential access while others are optimized for random access. And we also looked at the different access speeds between different storage types. We then talked about the database storage, the fact that databases need to manage data that far exceed the size of the main memory, and hence need to store some of the data, or mostly store the data on disk, but be able to move that data back and forth between disk and memory whenever it needs to access a certain part of the data. The component that handles all this is the storage manager, which lies right on top of the actual physical storage. It handles all these details without the other components having to know about that. Data is stored within files. Each database system has its own file format. The files are organized in terms of pages. There are different ways to organize the file. We've talked about heap files, hash files, tree files, and so on. Talking about the heap files in particular, heap files are used to store data pages. Pages are fixed size chunks of data. The heap file storage says that the pages have no particular order. Each heap file also stores a page directory which has some metadata about the pages in this file, how much free space, what is the location of every page, so that you can easily access a page given its ID. And then in the next video, we're going to get into the details of how is the page actually organized, and what does the page look like, and how the data tuples are organized within the page. So with that, I will see you in the next video, and thank you for watching.